Hello, and welcome back to the third video of our bite-sized integral calculus series where we are focusing on getting you a better grasp of first-year math integral calculus courses at your university or even in your high school if you're taking some integral level courses in your high school. So far in this video series, we have covered two videos. The first video was related to integration and the definition of integration as the area under the curve. And the second video was related to some examples which reinforce the idea of integration as indeed the area of the curve. And in this video, in the third video, we'll be discussing the relevance of differentiation with integration, how we can use the fundamentals or how we can use the techniques of differentiation that we learned in the previous math courses that we have done so far in the university or even in the high school, and how we can use those concepts in order to calculate the integral of a function, and that too without using any existing formula of integration that will come across in the later videos. So we'll start with this video, but if you want to take a closer look at the videos we uploaded in this playlist so far, you can always click on the I button above and watch those videos as well. And I would highly appreciate as well if you can watch those videos, because those videos will give you a better relevance of the upcoming topics that we'll be covering in this video series. So we'll start with differentiation versus integration. So in math or in general as well, differentiation and integration are considered to be the reverse processes of each other. So for example, if you want to differentiate the first function, you'll have to sort of come up with another example or another function, the second function, for which if you differentiate that second function, you'll get the first function that you wanted to integrate it. I know that sounds a bit confusing at the first sight. We'll move on to some certain examples which can reinforce this idea about differentiation being the reverse of integration, and we'll cover those ideas in the next slide. But the basic idea of this video and integration in general is to come up with a function for which if you differentiate that function, you'll get the original function that you were integrating. So let's move on to the first example that we have on the screen. Again, the most basic function that we have. So as you can see on the slide as well, on the left hand side you'll see a function, but on the right hand side you'll see the answer of the integration of the function. Also, please note that the formula or the answer that you see on the right hand side of the screen is calculated from the existing formulas of integration that we have, but will sort of confirm those existing answers of the integration of some functions by relating the concepts of differentiation that we have learned so far. So let's move on to the first example. The first example that you see on the screen is fx equals a, where a is a constant. A can be any real number. A can be 1, a can be 2. We covered this in the last video as well. So if you want to take a better look at what this function looks like, you can also watch the previous video, for which you can also click on the I button above as well. So let's move on to this function. So we want to integrate this function. Right now at this stage, I'm not using the notations that we have for representing integration, such as this symbol that we use for integration, because we'll cover those concepts in the upcoming videos. But the main idea of this question is to integrate a function fx equals a. So now, as we know from the previous slide that integration is indeed the reverse of differentiation, we have to sort of come up with a function for which if I differentiate that function, I'll get a as a result of my function. So we know from differentiation that if we differentiate a linear function, we get a constant, right? So based on the concepts that I know for differentiating linear functions, my first guess becomes ax, right? And that indeed relates to the existing answer that we have for integration as well. But in this answer, or in the guess that we have gotten so far, there is a catch in this. So we also realize one more thing about this function, or fx equals a, that even if I differentiate ax, I'll get a, but if I also differentiate another function which is something like ax plus 1, I'll also get a as my original function if I differentiate this function as well. And that also applies to ax minus 528. So in order to come up with a general solution for this problem, I'll also have to consider the fact that differentiation of constants is 0. So as a result, my most appropriate guess becomes ax plus c, where c is a constant. C is also known as the constant of integration, and we'll cover the significance of this constant of integration that we have on the screen represented by c. But as far as the scope of this video, you can consider c as a constant, and c is indeed a constant, and c belongs to any real value that you can assume. So in this example, we related the concepts of differentiation that we knew so far and used those concepts of differentiation in order to calculate the integral of a function. And you can also see on the screen as well This ax plus c solution that we got so far also matches to the existing answer that we have for integration. So this also serves as a confirmation that we can use differentiation in order to calculate the integral of a function. So now we'll move on to the next example, but before we move on to the next example, I would also like to mention an interesting observation that whatever correct guess will come up for a second function, we will always add this constant of integration at the end of that correct guess that we have so far. So now let's move on to the next example. The next example is also a simpler example. It's fx equals x, and in this example also we'll have to do the same thing. We have to come up with a second function for which if we differentiate that function, we get x at the end of differentiating that function. And I also know from the concepts of differentiation that if I differentiate a quadratic function, a function which is of order 2, I'll get a function which is of order 1. So my first guess becomes x squared, right? But what happens if I differentiate x square? If I differentiate x square, I get 2x as the answer, but I don't want 2x, I want x. So now I have realized that my guess is going on the right direction, but I just have to play with some constants in order to get my final answer. So I realized that x square gives me 2x, but if I differentiate x square by 2, it will give me x at the end. So x square by 2 appears to be the correct guess that I'll get after integrating x, but again the same thing. In order to get to the final solution, I'll have to also consider the constant of integration that we have. So now, since I've confirmed that the differentiation of x square by 2 gives me x, I'll just add a constant of integration at the end to get to my final solution. So that is why the final solution becomes x square by 2, which also relates to the existing answer of integration of x that we have on the right hand side of the screen. Now we'll cover another example just in case. So the next function is fx equals e to the power x. In this question also we have to do the same thing. We have to come up with a second function for which if we differentiate that function, we'll get e to the power x at the end, right? So what do we know about exponential functions? We know from the fact of differentiating exponential functions that if we differentiate an exponential function, it remains an exponential function. So my first case becomes an exponential function. So I'll start with e to the power x. And this appears to be the correct guess as well, because if I differentiate e to the power x, I'll get e to the power x again. So now the same thing again, since this appears to be the correct guess that we've got using differentiation, to get to the final solution, we'll add a constant of integration at the end. And that will give us the final solution to the integral of e to the power x, which can also be confirmed using the solution. So that was it for today's video. At the very end of this video, I'll leave you with some practice questions that you can solve, and I would highly appreciate that as well if you can comment down your answers to the problems that you see on the screen. So that was it for today's video. I hope you really liked the video. Follow the channel if you want to get notified about the other videos that we'll be uploading, and stay tuned. Thank you so much for watching. Bye bye.